the baseline, that's the comparison between business as usual and the baseline. Fortunately, we have offsets from both mitigation and adaptation. So mitigation reduces the severity of climate change. We don't have as much growth in greenhouse gases, and therefore we have capacity to that we don't experience the same degree of reduction in runoff. But also, and central to the model, farmers adapt by changing to less water-intensive land uses, by using water, as I've mentioned, in a more flexible fashion, responding to periods of high availability, which may become less common, responding to a less predictable and stable supply of water. So I'll just bring up the baseline simulation, and you can see the 18 regions in the model. This legend, I hope it's legible, gives us the economic value of agricultural output, or rather irrigated agricultural output in the various regions in the baseline, in the basin. And we can look at that in detail in terms of the allocation between alternative crops, typically with rice and cotton being grown in the northern part of the basin, lots of horticultural crops in the South Australian section, and a fair bit of dairy and pasture in the upstream Victorian sections. So this is the baseline simulation, a typical economic value of output of the order of $4 billion per year. Now, going to the opposite extreme, here's our climate change results for 2100 and in the absence of mitigation. Now, this is a model which it takes account of what adaptation farmers are able to undertake, but the answer is that the supply of water for irrigation in these simulations is so small that essentially there is no real capacity for adaptation here. The system converts entirely to dryland agriculture. We haven't modelled what happens to dryland agriculture with, of course, higher temperatures and reduced rainfall. This is largely work we've done for the Garnaut Review of Climate Change. In that context, we've been joined by a number of other modelling groups to feed in impacts on both irrigated and non-irrigated agriculture. That's then been fed into general equilibrium models to try and predict an overall impact. But what we see in this simulation just reinforces the basic point that I made at the beginning, that in the absence of mitigation, certainly in the context of irrigated agriculture in the Murray-Darling Basin, climate change will outrun any meaningful capacity for adaptation. Here's our simulation with mitigation at 550 parts per million. So that's been, I guess, the target that was certainly in vogue when we started doing this kind of modelling. It's mentioned a fair bit in the Stern Review of Climate Change. And what we see is that relative to the baseline case, there are quite significant reductions, but nothing like the kinds of losses that we saw in the case of business as usual. We also see a fair bit again of adaptation. We do have reduced runoff, and therefore we see in these simulations a fair bit of shift out of water-intensive sorts of activities, particularly dairy in the upstream parts of the region. This is the more ambitious target, 450 parts per million. This is what Ross Garnaut has been talking about to a large extent, and I think it reflects particularly, certainly in our modelling, the difference between 450 and 550 for agriculture is possibly not that great in the context of the Murray-Darling Basin, though it's significant. But certainly in terms of risks to do with extinction of natural extinction of species, loss of biodiversity, and sea level rise, increased frequency of cyclones and so forth. These seem to be the risks that have led an increasing focus on the question of whether we can reach mitigation of 450 parts per million. So that's a summing up of the, just a brief one of the research we've been doing on the interaction between adaptation and mitigation in the Murray-Darling Basin, and the lesson is quite clear that unless we have both, we're going to have a very unsatisfactory outcome. Now, I should say that while we've modelled, in the runs I've described, we've modelled on-farm adaptation, change in land and water use, we haven't modelled substantial changes in the institutions governing water use. And it's fairly clear that we're going to need those, and in fact research which we're just doing shows that we can get very substantial additional benefits if we take the kinds of steps that of course have been on the agenda for a very long time in Australian water policy, particularly with respect to the Murray-Darling, steps like allowing the purchase of water from irrigation for environmental flows, and more generally trying to equalise the social value of water between upstream and downstream users, rather than trying to keep water within the largely upstream catchments where local interests want to try and prevent water being taken out of those catchments, largely for institutional reasons that are summed up in the phrase stranded assets. I won't go into that in great detail, but clearly we can get, with full-scale adaptation, a substantially better response to climate change than with the on-farm adaptation alone that we've modelled here. So, to summarise, we need to, as far as mitigation is concerned, I think it's clear, as I've said, that adaptation is going to take place, possibly not optimal adaptation since we need a range of policy responses, but if climate changes one way or another, we will adapt. Mitigation is much less clear, and there's still quite a few people saying that it's really just a bit too hard. We need to stabilise global CO2 emissions below 550 parts per million, and then ideally to reduce them. That implies a minimum 60% cut in emissions by 2050. Recent discussions are looking at responses to the rapid growth in China and India, which have largely ruled out, I think, the kind of strategy where we cement permanent differences in per capita emissions. They've really pushed us towards a contract and converge type strategy that would entail deeper cuts in countries like Australia, up to 90% reductions in emissions. But we're still really doing the economic analysis on that, but I think it's clear from the analysis that's been done so far that we can in fact greatly reduce global CO2 emissions while still greatly improving living standards. So in this context, there have been a bunch of quite scary statements really from both sides of the debate. People like the Competitive Enterprise Institute, whose various videos you may have seen saying carbon dioxide, they call it pollution, we call it life, and similar excellent contributions to the debate. People who essentially are in the do-nothing camp have suggested that doing anything about climate change will be economically ruinous. And some people, I guess, on the pro side seem to view that prospect with equanimity. There are certainly people in the peak oil community who see us going back to the Middle Ages and think that will be a very good idea. No real economists, no serious economists in either of these groups. Economists are much more hopeful. So economists nearly all agree that the likely cost of 50% odd reductions in CO2 emissions by 2050 are in the range of 1 to 3% of income,